Okay, I got a couple questions about this, the difference between a vertical asymptote and a hole. And so I thought that I would just make a video explaining the ways that you kind of show work for these problems. Okay, I'm back and I grabbed this problem from your practice homework just so that we could have something to talk about. So the difference between a vertical asymptote and hole is just the way that they look graphically. The vertical asymptote is very disruptive to the graph. And so an example of this would be the graph for 1 over x. And it kind of looks like this. And so on either side, it has a vertical asymptote at 0. So it has this line at 0. And then on either side of this line, and right here, I would say, like right at this line that we're talking about, it has this huge kind of chasm where the graph is not connected and it's kind of radically different, right? Now, that's different than, let's say, the graph of x squared over x, which really will still have a discontinuity at 0, but otherwise will just kind of look like a normal, because this simplifies to just be x, but these are slightly different functions, right? This function on the left is not defined at 0. And the function at the right is. So, but they're almost the same. They're the exact same function, except at this point 0 where I have a hole. And otherwise, this just looks like a nice normal graph of x. I mean, it's not hard. It's a linear function with slope 1. Okay, so it turns out, so this is the picture of the behavior, of the two types of behavior that we want to see, kind of like the asymptotic behavior that's really disrupting the graph, versus this hole, which is just like, I just have to take this one point out and that's it, right? Okay. So, but these points, so one of the questions I got was, how do I know, like, where these could possibly be? And the answer is these are linked to part A where you find the domain. So for example, for part A in 8, you would say to find the domain, you would set the denominator equal to 0. And so the function cannot equal -4. So your domain is -4, or minus infinity to -4, and -4 to infinity. So this point right here, the problem point, is the place where the graph will either have a vertical asymptote or a hole. So for part B, the thing that I'm trying to find is really the limit as x goes to -4 from the right of f of x, and the limit as x goes to -4 from the left of f of x. Okay. And so in this class, we can find those limits by doing a table, maybe. Sorry, I have a little frog in my throat today. Or like, we really want to just find out if it's a vertical asymptote or hole, if that's the only question. There are 3 different types of work you could show in part B, right? Okay, so 1. Let's put this 1. You can do the k-test, right? I did the k-test in the video. You take and find f of -4 and see what form it is. So I plug -4. Now the denominator is always going to be 0. This is not a surprise. The question for the k-test is what the numerator was. And so this is in the form k over 0. So that means that it's a vertical asymptote. K being anything that's not 0. If I get 0 over 0 out of the k-test, that test is inconclusive. And I have to look at the factored form to see what's going on. And we'll do that test in a second. And I'll show you, I have a second example too. So 2, you can do a t-table. This option 2 gives you the most information when you go to graph. So I'll do the limit as x goes to -4 from the right of f of x. And you're going to do 2 tables because you want to go from the right and left. You have to analyze this directional behavior. So x. When I'm going -4 from the right, let me picture this just to make sure, because when I'm in the negatives, sometimes it's hard. So over here is -3. Over here is -5 in the negative direction. So -4 from the right is right here. It's like a -3.9. And from the left is over here. It's like -4.1. Okay, so from the right, -3.9, 3.99. And while I'm thinking about it, I'm going to set this up. Okay. And then you can plug this into your calculator. Let me find mine. I lost it somewhere. Okay. Into the original function, which should be, it's x minus 5 over x plus 4. So I'll do that real quick. So I have -3.9 minus 5 divided by I get -89. I need to find the other calculator. This one is not the one that I like. Okay, and then I'm doing it for 3.99. Plus 4. And -899. So do you see how this, I'm only going to do 2 points, even though I know in the example video I did a whole bunch more. But like on the exam or on your assignments, 2 points is enough. If you know something weird is happening, to kind of give you a sense of the behavior right around this point. So the conclusion I draw, which I'll write up here, is that this thing is going towards -infinity. Do you see how it's getting big and really negative? Okay. So and then if I make that conclusion, that indicates to me that it should be a vertical asymptote. Holes go to an actual number. And we're going to do an example that looks like that, so don't. Okay, I plugged in and I get 9, 10, oops, hold on, that's not right. 91, not 910, but I bet I'm going to get 910 or something around 910 for this other one. Oh, 901, okay. So this is getting really big in the positive direction, so that means this is going to infinity. And so you can write, like you can provide this work on your table and say because of the table results, f of x has a vertical asymptote at x equal to -4. And up here you might write, I'm going to write these sentences that you might write. So by the k-test, I know f of x has a vertical asymptote at x equal to -4. You have to show the k-test. You can't just pretend that you did it or have it somewhere in like Fantasyland. Oh, and then I want to do, one more. There's one more way to kind of show this, and this is just to look at the factored form really, and we'll see this more clearly with the next example, but the problem is coming from this denominator where it's 0. So if I had x plus 4 in the numerator, I could cancel them. If I can't cancel x plus 4, then this is a vertical asymptote. If I can fully cancel, and there's no more x plus 4's in the denominator, then this is a whole. Then this is a whole. Yeah, that's what I want to say. So in this case, there's no x plus 4 in the numerator that allows me to cancel. So here the sentence would be, I looked at the factored form of f, and x plus 4 does not cancel. With a factor in the numerator. So f of x has a vertical asymptote at x equal to -4. Okay? Okay, now we're going to look at this next example where it does cancel. Okay, so I'm going to do the same thing, right? So I'm going to say, again, this is related to part A with the domain. Here, the problem point is at 3, right? So when I go to look at these 3 ways, I'm going to do the same ways, right? So 1, the k-test. So I'm going to find f of 3. And that will give me 9 minus 18 plus 9. 0 over 0. So here the k-test is inconclusive. 0 over 0 honestly tells you nothing. It tells you there might be a hole, but honestly you don't know. So you have to do one of the other 2 tests. The k-test is really great for identifying very quickly vertical asymptotes, but nothing else. 2. Let's do this t-table. Okay. So on 3, I'm a little bit more solid. The limit, I'll write the limit down here. Limit as x goes to 3 from the right of f of x. And over here, limit as x goes to 3 from the left of f of x. Okay. So from the right, that's 3.1, 3.01. From the left is 2.9, 2.99. And I'm going to put that into my calculator. With the numerator and denominator in parentheses to make sure. I don't want to do that. And I get 0.1. I'm going to put in 3.01. And then 0.001. Do you see how this is not getting to be a huge number? It's just getting to be a small number. I'm going to put in one more number to make sure that and then I'll show you how to I think I exaggerated. This must be 0.01. I'm going to check this one because I'm getting the same answer here and I do not. Oh yeah. Okay, so this is what the chart looks like. And I'm going to do it for 2.9. Negative 0.1. negative 0.01, and I'm going to do one more. Negative 0.001. Now, you see, these aren't getting really big. The vertical asymptotic behavior has to go to infinity or minus infinity. These look like, if I had this is going to 0, and on this side it's going to 0 from the negative side. So out of these, I think my limits are both going to 0. Now, because of that, do you see how 0, and 0 is kind of like not special. In this case, it's just a number, but it's a solid number. It's not like infinity and getting really big. So because of this, I conclude, because I think that the limit as x goes to 3 of f of x is equal to 0, then f of x has a hole at the point 3, 0. Right? So this is the sort of behavior that you see when there's a hole. Now, I think the third test is the most conclusive, and I'll show it because it makes you just feel like you absolutely know what's happening. So here's, let me check and make sure that this is the right function and I haven't switched any signs, right? Okay, so I'm just going to look at, this limit as x goes to 3, right, of this function. And really, do you see that the top factors to be x minus 3 times x minus 3? So this is what I'm talking about in the third test when I say, look, if you factor it, and you see these can cancel in factored form. So this limit is really the limit as x goes to 3 of x minus 3 without this thing in the denominator. And so this is the number 0, right, when I plug in 3. Which is completely fine. Again, this tells me, this line here where I cancel tells me that there's a hole. So do you see that? Like before we had this x minus 5 over x plus 4, and I couldn't cancel. They weren't the same. So that's a vertical asymptote. Over here where they do cancel and there's nothing, this x minus 3 is not left in the denominator. That means there's a hole at that one, right? So because the factor x minus 3 cancels in the denominator, there's a hole at x is equal to 3 and y is equal to 0, where this limit that you found is the y value. Okay? So I hope this helps as you're working on your homework over the weekend or on Monday to just kind of figure out what's going on with these problems.